So before we go into the solution of this, I have a very short question for you. Imagine a body is moving in the xy plane here. Its momentum is always the same in length, but the direction of that momentum is constantly changing. Momentum is same in length, but the direction of that momentum is constantly changing. What does this tell about the motion of that object? And for this condition to be satisfied by the object, that is an object moving in xy plane with same length of momentum and different direction, what kind of force should be causing this motion? The point here is to visualize what is given in this question here. Well, of course, I just asked you in a different way. The theme remains the same. Now pause the solution here, take a couple of minutes and think of this, okay, and try to visualize the given condition here. So I'm assuming you have done that, in which case, let us now dive into the question. So the given question gives us a vector function, momentum vector, vector p is equal to px I cap plus py j cap, where px is cos kt, which stands for the x component of momentum, and py is minus sine kt, which stands for the y component of momentum. What do we mean by the length of a vector? Why is this relevant? Because we've been given this momentum vector here. So what do we mean by the length of a vector? So when we say magnitude of vector, should be more precise here, magnitude of momentum vector, oops, my bad. When we say magnitude of momentum vector, we're talking about the magnitude or size or length of that vector. So basically, if we were to draw one vector like this, length of vector, length of vector, or the size of this vector is what we call as magnitude of the vector, which literally would mean how long is this arrow. In 2D vectors, the magnitude of a vector is given by, if the vector is vector p is equal to ax I cap plus ay j cap, then the magnitude of the vector is given by root of ax squared plus ay squared. For example, if vector a is 3i plus 4j, magnitude of vector a would be root of 3 squared plus 4 squared, which is 5. Therefore, magnitude of vector a is 5. Now, why are we talking about this? Well, there's more into it. So what do we mean by length of a vector? Root of modulus of vector, which is root of x component square plus y component square. The x component here is cos kt, y is sine minus sine kt, so this is cos square kt plus sine square kt. Now we know that cos square theta plus sine square theta is 1, and therefore root of 1 is 1, which means the magnitude of this momentum vector here, p of t, is equal to 1. The length of the vector here is always equal to 1, no matter what time it is. There might be a very significant amount of lack of clarity in this statement. Length of vector is always 1, no matter what time it is. Well, let's just spend some more time to understand what that means. So we just found out that magnitude of the momentum vector p of t is equal to 1. This tells us that the speed of the object is not changing and only its direction is. What would that mean? Vector p, magnitude of vector p is a constant. This actually means that Momentum vector, which is equal to mass into velocity vector, has two components. One which is mass, which is a constant, and then velocity vector, which has both magnitude and direction. Okay, so mass itself is a constant, and then on top of it, we have velocity vector, which will have magnitude and direction as well. Now, this magnitude is a constant, direction is varying. So when we say speed is constant, it is this magnitude that we say is constant. Now you might be thinking, come on, magnitude is always a constant, isn't it? And that's where I said the difference between a mass as a constant and this vector magnitude as a constant is a bit different. It's slightly different, but that's significant enough. Let's see how. So if magnitude of momentum vector is a constant, velocity is a constant. And since velocity is a constant, speed has to be constant. Okay. So in this case, since magnitude of p is 1, at all times, the speed of the particle does not change, but the direction of the particle does change. Another question that you might have in your mind. Doesn't every vector has a constant magnitude, because a vector would have magnitude and direction as well, and that magnitude will always be a constant? Well, actually, no. Why? Let's see that. Vector A is equal to AXI plus AYJ, and magnitude of this vector would be constant in all cases, is what we generally think of. Now, to understand this, let us take a couple of examples and compare what these two means. So, example one, what is given in our problem here? Momentum vector P of t is I cos kt minus sine kt, and this is of constant magnitude. Why? Because when you take magnitude of this vector, we get 1, which is a constant, which is not surprising. But if we have a different vector, say vector q of t is equal to it plus jt square, when you take magnitude of this vector, vector q of t, you get t times root of 1 plus t square. This actually means that the magnitude of vector q of t, which is actually equal to q, is a function of time and the product of 1 plus t square. To be more precise, q at t is equal to 0 will give you q1, or say q0, which would be 0 into root of 1 plus 0 square. And then you have q1, which is 1 into root of 1 plus 1 square, so on and so forth. Which means this is not a constant. It grows over time. It is dependent on time. Unlike the first example, as in the given problem, it is a constant always. So the magnitude of this momentum vector here is constant always. Okay. Right. So now if you have understood this concept and the slight difference in it, let us now try to understand what is this P of t really. So the momentum vector P of t is I cos kt minus j sin kt. We understand that the I component cos kt is px and the j component minus sin kt is py. So this is just like a 2D arrow whose head moves around, first pointing towards right, then to downwards, then left, and then upwards. Now, what kind of motion is this? If you would make a guess, exactly this would give you a rotating arrow. Now, there is a minor error in this diagram here, and I would suggest you find it out. What is the mistake in this arrow here? Okay. Now, at t is equal to 0, the arrow point towards right, the arrow point towards right like this. As t increases, the arrow rotates clockwise. It traces a perfect circle in the xy plane. This momentum vector is rotating, and how it would be rotating with this magnitude being equal to 1. Of course, in which plane? In the xy plane. Okay. So we have a motion which has constant speed, continuously changing direction, and the rotating momentum vector, and we directly know that this motion is a uniform circular motion. Now, which force will cause this kind of a motion? Well, that depends. In case of planetary motion, the force which causes this is the gravitational motion. In the case of electrons revolving around the nucleus, this is, of course, the nuclear force. In the case of a car moving around in a circular path, this would be the force of friction. And we have many such examples like that. Now, in a uniform circular motion, we know that the speed is constant, the direction is changing, and therefore the velocity is not constant, right? Combining these two, the velocity is not constant. Constant speed is constant, but due to changing direction, velocity is not a constant. So there must be a force acting in this case as well. Why? Come on, of course. Why? Because if there is no force, the momentum should stay in the same direction. If momentum is in the same direction, then the velocity vector should also be the same direction, which is not the case here. Why? Because the velocity vector is changing. And if the velocity vector is changing, it means that there is some force that is causing this velocity vector to change. Now, what is that force which is causing this rotation? Now, I do understand that you might be thinking this is not what actually is being asked in the problem. This is not what the option stands for. But the point is, we're trying to appreciate what the concept is, is being evaluated here. That underlies the question, and why? As usual, this these kind of questions, which have an underlying concept, give rises to a potential question in the coming JE means or need for that matter, which may not be a similar one based on a numerical, which instead may be from from the same concept, but rather would be a statement one, statement two type of question, or maybe assertion reasoning. Okay, so the concept is really important. Now, how do we find the force? We find the force by differentiating what? Differentiating the given vector, the momentum vector. Why? Because we know force is rate of change of momentum. And to be more precise, vect F is the rate of change of momentum vector. What is momentum vector given to us as? I cos kt minus j sin kt. Derivative of cos t is minus sin t. Derivative of sin t is plus cos t. So dp by dt gives us force vector, which is minus k I sin kt plus j cos kt. I've just made a minor rearrangement with taking this negative one outside the brackets. So we get f of t is equal to minus k into I sin kt plus j cos kt. Okay. Now, the interpretation here. First, let us say about the minus sign. The negative sign in front of this is extremely meaningful. Now, you might be wondering what's so meaningful about just a small, a minor minus sign that is included here. Well, that's where the concept makes it really important. Why? Because if we ignore this minus for a second, the term inside the bracket, which is I sin kt plus j cos kt, this one here, or maybe I should take this as a reference. So when I say the term inside the brackets, what I mean is, okay, what I mean is this one, I sine kt plus j cos kt. If we ignore the minus for a second, if we ignore this minus, so ignore this minus for a second, the term inside the bracket, which is I sine kt plus j cos kt in the expansion of, in the expression of f of t, is actually a rotated 90 degree, is actually a vector, which is the rotated 90-degree one of this momentum vector, or vector f without this minus k is vector p rotated 90-degree ahead. Some of us might still be finding this confusing. Make it more clear. When we multiply it by negative, the direction flips. The direction flips like this. So it becomes 90-degree behind the momentum vector. Okay, now I understand that it's more confusing. If you haven't been writing this along with me, I would say you can start doing that now. It's a very humble request because this is where I expect a future question. Well, of course, I can't predict that, but if it is based on, if a question in the future is based on this question, this is where it would make sense. So the momentum vector is I cos kt minus j sine kt. This is a standard circular vector. It has the form cos, comma minus sign. This means it points tangentially along the motion. So along the circular motion, at this point, tangential is the direction of velocity, and therefore the momentum vector would also be in that same direction. It will be tangential at this point, and therefore the momentum vector would be tangential to the velocity, the corresponding point. So if this point is C, the momentum vector at C would be equal to mass times velocity vector at C, which is tangential to the point C. Likewise, point D, velocity at D times mass will give you the momentum vector at D, which will be tangential to that point. Now, differentiation gives us the force. Okay, let me just make it more clear for you. So we had momentum vector P. When we differentiated the momentum vector, what we got was vector F, which was equal to minus K times a different vector, vector A. Now we will talk about that vector, vector A. The vector A is minus sine kt plus j cos kt. The vector is important. Why? Because it is a vector which is rotated 90-degree ahead of the momentum direction. Which means if this is the center of circular motion, and let's say this is point 1, and if P1 represents the momentum vector at 1, then vector A is 90-degree ahead of the momentum vector, which means it is this 90-degree that we are talking about. So vector A is 90-degree ahead of this vector. Why? Because rotating a tangent vector by 90-degree gives the outward normal. Now, this is where very particularly I feel that you might have a question. And therefore, writing down this becomes really important. Yes, I do understand that we're taking a lot of time for a very small question, but we're not trying to solve just the question. We're also trying to understand the concept. Again, why? This might be the future question. So, are we done? No, because this is not what we should be really talking about, because we are not talking about the vector A alone. We need to specify our thoughts regarding vector F, which would be like this. If we ignore the minus sign, right? If we ignore the minus sign, without the minus sign, we get this vector, vector A, that is acting normal. But if we include the minus sign as well, what we get is a vector which is now pointing inwards instead of the vector pointing outwards, which is vector A. So we have momentum vector, vector P. Vector A was a vector that is ahead of momentum vector by 90 degree. Now what we get is an inward radial vector, which is perpendicular to the tangential vector, momentum vector. And this inward radial vector will give you the direction of force, which is contributing this circular motion. Also, the angle between vector F and the momentum vector is 90 degree here. Why would that be important? Because if we take the dot product, vector F dot vector V or vector F dot vector P in both cases, magnitude of the dot product would be magnitude of vector F, which is F, magnitude of vector V, which is P, into cos 90, which is 0, and therefore the dot product is 0. So if F dot V is 0, definitely it also stands for F dot, the momentum vector is also equal to 0, right? So it also means that something else is equal to 0. Can you just make a guess of what it would be? F dot velocity, momentum. So there is something else that acts in the same direction. What would that be? Think of it. Coming to the next important one, the phrase in the expression, which is K. How would K influence the vector? If the value of K increases, the momentum vector, it will rotate faster. So small k would be like this. If it if it increases, say for larger values of k, the momentum vector value would rotate, it would increase fastly, which means it would turn more sharply. The rate of change of direction would increase. Now, when I say rate of change of direction, it means 0 second, 1 second, 2 second, 3 second, 4 second, like that. It would increase dramatically. And therefore, the magnitude of force will also increase to withstand this change in momentum. If you double the rotation rate, you will double the required inward pull. Now, so to summarize this, negative sign indicates the force is directed inwards, which means towards the center, radially inwards, and K tells us how fast the direction changes. Or in other words, indication of what? Indication of angular speed. Okay. If you haven't been following the suggestion to make notes, I would suggest please at least make a note of this table, because I have summarized almost all the things that I've discussed so far. And yes, a very potential question from this table. Okay. And if you're also thinking about what I asked you to, it would give you that the work done, which is vector F dot vector S, is also equal to 0. So F is radially inwards, speed stays constant, F is larger speed. Okay, we discussed all those. Now, coming to this question. See, this is a beautiful question. I mean, I just can't emphasize much on how significant this is. Seems to, on the face of it, this seems to be like a very good question and a very simple one. But the concepts underlying this, and Mind you, this is a very decent question. It appeared in 2024. And I would say this can be solved in it can be solved using four different concepts that we learn in three different chapters. And therefore, the beauty to it. Okay.